So in the last lecture, we talked about a graphical tool for solving small linear programs. So this graphical tool for solving small linear programs was useful when we're dealing with linear programs with 2 decision variables, maybe 3 decision variables, but that's about it. So what we're going to do in today's lecture is we're going to talk about some linear algebra concepts. And these linear algebra concepts are going to be very useful in the next lecture when we will be developing an algorithm to solve large linear programs with as many decision variables as we like and as many constraints as we like. Okay, so again, our goal is to talk about linear algebra concepts today with the understanding that these linear algebra concepts are going to be useful just right in the next lecture when we're going to be developing an algorithm to solve large linear programs. Okay. And the linear algebra concepts that we're going to be talking about today should be familiar to most of us, especially for sitting in this course. But nevertheless, it's good to keep these linear algebra concepts fresh. All right, so let's first start talking about matrices. So let's talk about matrices. So let's say an m by n matrix. When I say an m by n matrix, this matrix has m rows and n columns. Let's say an m by n matrix A has m rows and n columns. Okay, and at risk of boring you, let's write down a matrix. Let's write down a 4 by 3 matrix. A 4 by 3 matrix is going to have 4 rows and 3 columns. And let's say this 4 by 3 matrix is going to look like this. So this is a 4 by 3 matrix. This matrix has 4 rows and 3 columns. Good. If I have an m by n matrix A, and if I take its transpose, the transpose of this m by n matrix, it's going to be an n by m matrix. And when I take the transpose of a matrix, its rows become its columns. So let's say if A is an m by n matrix, then its transpose, and we denote the transpose of a matrix as A superscript T. If A is an m by n matrix, then its transpose is n by m. And when I take the transpose of a matrix, its rows become its columns. Let's take an example again. Let's take the matrix that we put on the right up above. 1, 2, 3, 3, 1, 7, 1, 4, 2, 4, 5, 1. So this is a matrix that is of the size 4 by 3 we said. 4 rows and 3 columns. When I write down the transpose of this matrix, it's going to be a 3 by 4 matrix, 3 rows and 4 columns. And the rows of my original matrix are going to be its columns in the transpose. Good. So this is how we write down the transpose of a matrix. So lastly, let's talk about the identity matrix. An n by n identity matrix, is a square matrix, has ones in its diagonals and zeros in the off diagonals. An n by n identity matrix. And we usually use the capital I to denote an identity matrix. An n by n identity matrix I has ones in the diagonals and zeros in off diagonals. And here's an example of an identity matrix. Here's an example of a 4 by 4 identity matrix. Ones in the diagonals and 0 everywhere else in the off diagonals. And this is again a 4 by 4 identity matrix. Great. Now, hopefully these are extremely familiar. These are almost the point that they're getting boring. But I'm going to say a few more boring things, but then things may get interesting. Let's talk about matrix operations. Good. If I have two matrices of the same size, we can add these matrices. So let's say if A is m by n and B is m by n, then I can add those matrices up. And A plus B, the addition, the sum matrix, is also m by n. And matrix multiplication is super easy. When I'm adding two matrices, I just add up the corresponding components. Let's do a simple example. Let's take a 3x4 matrix. 1, 2, 4, 1, 3, 4, 2, 5, 5, 1, 3, 4. So this is a 3x4 matrix. Let's take another 3x4 matrix and add those two up. Minus 1, 4, 2, 0, 1, 3, 1, 5, 4, minus 2, 6, 1. That's another 3x4 matrix. And let's add them up. The sum is also going to be a 3x4 matrix. Good. And in the sum matrix, first row, first column, just take the corresponding entries and add them up. 1 plus minus 1 is 0. 2 plus 4 is 6. 4 plus 2 is another 6. 1 plus 0 is another 1. 3 plus 1 is 4. 4 plus 3 is 7. 3 plus 1 is 4. 4 plus 3 is 7. 2 plus 1 is 3. 5 plus 5 is 10. There is a 9 here. There is a minus 1. 1 plus negative 1 is minus 1. 3 plus 6 is 9. 4 plus 1 is 5. So this is how we multiply matrices. Not terribly interesting. Let's talk about one more concept that's probably quite simple, and then things are going to get interesting. We can also think about matrix multiplication. If A is m by r, if A is m by r, and B is r by n. So their inner sizes match. If A is m by r and B is r by n, then I can multiply these two matrices, and their product is going to be m by n. I can multiply two matrices when their inner dimension matches. When I multiply the two matrices, I obtain a new matrix whose dimension is equal to the outer dimensions, if you like. And let's remind ourselves how the matrix multiplication works. Let's take a 3x4 matrix. And let's take a 4x2 matrix. And the inner dimensions of these two matrices match, so we can multiply that. And if you multiply these two matrices, the dimension of the matrix that we end up in is going to be 3x2. 3 rows, 2 columns. Okay, let's take an example. Let's say my 3x4 matrix is 1, 3, 4, 2, 2, 4, 1, 3, 5, 1, 2, 3. Let's take my 4x2 matrix and let's say this looks like 2, 3, 1, 1, 1, negative 1, 4, 2. Let's multiply these matrices and let's see what we end up with. So I'm filling in the, so this is 3x4, this is 4x2. So the matrix multiplication is going to give me a 3x2 matrix, 3x2 matrix. 3 rows, 2 columns. Good. So I'm looking at the product matrix in the first row, first column. I take the first row here, I take the first column here, multiply the corresponding entries and add them up. 1 times 2 plus 3 times 1 plus 4 times 1 plus 4, 2 times 4. Let's do the arithmetic. That's a 2 plus another 3. That's a 5 plus another 4. That's a 9 plus another 8. That's a 17. That's what we end up in the first row, first column. Let's fill this entry in. That is first row, second column. Take the first row here, second column here, multiply the corresponding entries and add them up. 1 times 3, 3 times 1, 4 times negative 1, 2 times 2. Add those up. That's a 3 plus another 3, that's a 6, plus another -4, that's a 2, plus another 4, that's a 6. Let's keep going. So now I'm looking at the entry that is in row 2, column 1, row 2, column 1, row 2 here, column 1 here, row 2 here, column 1 here. Multiply corresponding entries and add them up. 2 times 2, that's a 4, plus another 4, plus another 1, plus another 12. 4 plus 4 is 8, another 1 is 9, plus another 12, that's 21. Entry in second row, second column, second row here, second column here. That's a 6, plus another 4, that's a 10, minus 1, that's a 9, plus another 6, 9 plus 6, that's 15. Let's get this one, third row, first column, third row here, first column here, multiply the corresponding entries and add them up. 5 times 2 is a 10, plus another 1, that's 11, plus another 2, that's 13, plus another 12, that's 25. Let's fill this entry in. Third row, second column, third row, second column, third row in the first matrix, second column in the second matrix. Multiply the corresponding entries, add them up. 15 plus another one, 16, minus 2, that's a 14, plus another 6, 20. Okay, so that's how we multiply two matrices. And one of the useful things about matrix multiplication is we can use matrix multiplication to represent systems of linear equations. Let's remind ourselves how we can use matrix multiplication to represent systems of linear equations. Let's take a system of linear equations. 5x1 plus 6x2 plus 3x3 plus x4 equals 7. 6x1, 2x2 plus 4x4 equals 8. Here in the second equation, x3 is appearing with a coefficient of 0. 9x1 plus 6x3 plus 2x4 equals 1. So this is a system of linear equations with 4 variables and 3 equations. And let's represent the system of linear equations in matrix notation. So what we're going to do is we're going to take the coefficients of my variables and put them into a matrix. And I have 3 equations, 4 variables. So I'm going to need a 3 by 4 matrix. And put the coefficients of our variables in this matrix. 6, 5, 6, 3, 1, 5, 6, 3, 1, 6, 2, 0, 4, 9, 0, 6, 2. Okay, so this is a, what did we say? 3 by 4 matrix. And put our decision variables in another matrix. And the size of that matrix is going to be 4 by 1. And to put the right-hand sides in another matrix, and the size of that matrix is going to be 3 by 1. Good. Let's see what this says. I'm taking 2 matrices, multiplying them up and adding up, equating to the right-hand side matrix here. This is a 3 by 4 matrix. This is a 4 by 1 matrix. The inner dimensions match, so I can multiply these 2 matrices. And when I multiply these 2 matrices, I will end up with a matrix that's of the size 3 by 1. Let's write that 3 by 1 matrix. This is going to be a matrix that is 3 by 1. Okay, so it's got 3 rows and 1 columns. Let's find the entry in the first row, first column. If you want to do that, you get the first row here, first column here, multiply the corresponding entries and add them up. 5x1 plus 6x2 plus 3x3 plus 1x4. That is going to be entry in the multiplication matrix. That's in row 1, column 1. 5x1 plus 6x2 plus 3x3 plus 1x4. Likewise, let's compute the entry in the multiplication matrix that is in row 2, column 1. So in order to do that, take the second row, row 2 in the first matrix, column 1 in the second matrix, multiply the corresponding entries, add them up. 6x1, 2x2, 0x3, 4x4. 6x1, 2x2, 0x3, and 4x4. And lastly, let's compute in the multiplication matrix the third row and the first column. In order to do that, I'm going to take third row and the first column. I'm going to take the third row in the first matrix, first column in the second matrix, multiply the corresponding entries, add them up. 9x1, 0x2, 6x3, 2x4, add it all up. 9x1, 0x2, 6x3, plus 2x4, add it all up. So this times this is giving me this matrix. It's a 3x1 matrix. And what am I doing? I'm taking this time, this, and setting it up to the right-hand side. So now what this is telling me is this number should be equal to this should be equal to this should be equal to this. That's exactly what this system of equations is telling. 5x1 plus 6x2 plus 3x3 plus x4 equals 7. That's exactly what it's over here. 6x1 plus 2x2 plus 4x4 equals 8. That's exactly what it's saying here. So then we can represent this system of equations in this matrix form, this system of linear equations in this matrix form. And that sometimes becomes useful. So that's good to keep that in mind. Good. Okay, so now things are going to get interesting. So a lot of the things that we talked about so far were probably simple things that you've seen in the past. Things are going to be somewhat more, things are going to get somewhat interesting. Let's talk about matrix inversion. So if I have an, let's talk about matrix inversion. If I have an n by n matrix, and if this matrix is invertible, let's talk about how we can compute the inverse of this matrix. So if A is an n by n matrix, and it is invertible, and it's invertible. A is an n by n matrix, and it's invertible. Then its inverse, and we denote the inverse of a matrix as A superscript minus 1. If A is an n by n matrix and it's invertible, that's inverse A negative A to the superscript negative 1. Its inverse is also an n by n matrix, and it satisfies if I take a matrix and multiply it with its inverse from the left or from the right, I end up with the identity matrix. Okay. So that's what an inverse of a matrix is. The question is, how do we compute the inverse of a matrix? Right? There are many, many different ways computing an inverse of a matrix, but one particular way of computing the inverse of a matrix is going to be extremely useful from the perspective of solving linear programs. And that way of computing the inverse of a matrix is through doing row operations. So let's remind ourselves how we compute the inverse of a matrix by doing row operations. Say we are given the n by n matrix A, and we want to compute the inverse of this matrix. How do we compute the inverse of this matrix? By doing row operations. Let's remind ourselves. Okay, here's what we do. I have my n by n matrix. I write my n by n matrix, and right next to it, I write the identity matrix and put those two things into one big matrix. This is an n by n matrix. Next to it, I put another n by n matrix. So this is now an n by 2n matrix, n rows and 2n columns. And on this big matrix, n by 2n matrix, I apply some row operations. I apply some row operations to turn the left-hand side into the identity matrix. When I do that, the right-hand side is going to turn into some matrix. Let's call that the matrix B. So I have this A matrix, right next to it, we wrote the identity matrix. I take this big matrix and apply some row operations on it such that the left-hand side turns into an identity. The right-hand side is going to turn into some other matrix B. I don't know what that is. But if you do that, it turns out the inverse of A is given by this matrix B. So then let's say A inverse is given by B. Okay. And what do we mean by applying row operations on a matrix? row operations on a matrix, applying row operations on a matrix means multiplying the row of a matrix by a constant, or multiplying the row of a matrix by a constant and adding it onto another row. Okay, so those are the row operations. Row operations on a matrix is multiplying the row of a matrix by a constant, or multiplying the row of a matrix by a constant and adding it into another row. So let's do an example just so that we're refreshing these ideas in our minds. Let's do an example to remind ourselves how we compute the inverse of a matrix by doing row operations. So let's compute the inverse of a 3 by 3 matrix. So compute the inverse of. Let's compute the inverse of this matrix. A given by 1, 2, 2, 2, negative 1, 1, 1, 0, 2. Let's compute the inverse of this matrix. Good. What do? I'm going to take this matrix, 3 by 3, right next to it, the 3 by 3 identity matrix. So that's 1, 2, 2, 2, negative 1, 1, 1, 0, 2. Next to it, let's write down the identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. Good. So now ready to go. So now what we're going to do is we're going to apply some row operations on this big matrix, so that the left-hand side turns into an identity. I want the left-hand side look like the identity matrix. Here's one systematic way of applying row operations on this matrix so that the left-hand side turns into an identity. We're going to go column by column. We're going to first turn this column into 1, 0, 0. Then we're going to turn this column into 0, 1, 0. Then we're going to turn this column into 0, 0, 1. So that's what we're going to do. So I want to turn this column into 1, 0, 0. I already have a 1 here. That makes me happy. I want a 0 here. To have a 0 here, I'm going to take the first row, multiply by negative 2, and add it into this row. In that case, this number is going to turn into 0. So now my first row operation I'm going to apply is take the first row, multiply that by negative 2, and add it to the second row. And likewise, I want 0 appearing here. I want this 1, 0, 0. I want 0 appearing here. In order to do that, we're going to take the first row, multiply it by negative 1, add it to the third row. In that case, this number is going to turn into a 0. Take the first row, multiply by negative 1, add it to the third row. So let's do those two row operations and see what we get. I want blue. Good. One times negative 2 is negative 2 plus another 2. That's a 0. That's what I wanted anyway. 2 times negative 2, so you're going to multiply the whole row by negative 2 and add it to the second row. 2 times negative 2 is negative 4 plus another negative 1. That is going to give us minus 5. Let's keep finishing those row operations. 2 times negative 2 is negative 4 plus another 1. That's going to give us negative 3. Apply the whole row operations to the whole row. 2 times negative 1 is negative 2 plus another 0 is negative 2. 0 times negative 2 is 0 plus another 1, 1. 0 times negative 2 is 0 plus another 0. That's a 0. We took care of the row operations that we're applying on the second row. Let's apply row operations on the third row. Take the first row, multiply by negative 1, add it to the third row. 1 times negative 1 is negative 1 plus another 1. That's a 0. I wanted a 0 here anyway. That's exactly what I wanted. 2 times negative 1 is negative 2 plus another 0, negative 2. 2 times negative 1 is 2 times negative 1 is 2 times negative 1 is negative 2 plus another 2. That's going to give me a 0. 1 times negative 1 is negative 1 plus another 0 is negative 1. 0 times negative 1 is 0 plus another 0 is 0. 0 times negative 1 is 0 plus another 1, 1. And keep the first row of the matrix as it is. So now I made progress. I turned the first column into all 1, 0, 0. So the left-hand side is starting to look like identity. So now I'm going to focus on the second column and try the second column into an identity. I'm sorry, try to turn the second column into what I would get in an identity. So I want the second column to look like 0, 1, 0. So I want this number to look like a 1. So I'm going to take the second row and multiply that by minus 1 over 5. So this number is going to turn into a 1, so that I'm going to get closer to an identity. Let's do that. Keep everything as it is. But just take the second row, multiply it by a constant. That's row operations. Multiplied by -1/5 constant. 0 times -1/5 is 0. -5 times -1/5 is 1. That's exactly why I'm doing this. I want to have a 1 here. -3 times -1/5 is 3/5. -2 times -1/5 is 2/5. 1 times -1/5 is -1/5. 0 times -1/5 is 0. That's a 2/5. Great. So some progress is being made. So next, again, I want this column to look like what I would have seen in our identity matrix. So I want this to read 0, 1, 0. I want these things to be 0, 1, 0. In order to do that, what we're going to do is we're going to take this row, multiply by -2, and add it to the first row. And then we're going to take this row, multiply by 2, and add it to the third row. In that case, this is going to turn into a 0. This is going to turn into a 0. Let's do that. 0 times -2 is a 0. So let's add this, multiply this row by -2, add it to the first row. 0 times -2 is 0, plus another 1, that's a 1. 2 times -2 is -2, plus another 2, that's a 0. That's exactly what I wanted. -2 times 3/5, -6/5, plus another 2. -2 times 3/5, that is -6/5, plus another 2 is going to give me -6/5 plus 10/5, that is a 4/5. Good. Keep going. -2/5 times -2, that is -4/5, plus another 1. -4/5 plus another 5, -4/5 plus another 5/5, that is 1/5. Let's keep going. -1/5 times -2, that's 2/5, plus another 0, 2/5. 0 times -2 is 0, plus another 0, that's a 0. Likewise, we're going to take this row, multiply it by +2, and add it to the third row. That's the other row operation we're doing. 0 times 2 is a 0, plus another 0, it's a 0. 1 times 2 is 2, plus another -2, that's a 0. 3/5 times 2, that's 6/5, plus another 0, that's a 6/5. 2 times 2/5 is 4/5, minus 1. 4/5 minus 1. 4/5 minus 5/5, that is -1/5. Keep going. 1/5 times 2. I'm sorry, 2 times -1/5. 2 times -1/5, minus 2/5. And lastly, 2 times 0, it's a 0, plus another 1. That's just a 1. And keep this row as it is. We're making a lot of progress. So now this looks like what I would have liked to see in an identity. This looks like what I would like to see, what I would like to have seen in an identity. So now we need to turn this into what I would like, what I would have liked to see in an identity. So in particular, I want this column to read 0, 1, 1. I'm sorry, I want this column to read 0, 0, 1. If I want this to look like identity, I want the last column to read 0, 0, 1. So now I want to turn this into a 1. In order to do that, let's take this row and multiply that by 5/6. Let's do the other row operations here in this side. Okay. Keep everything as it is. Just multiply the last row by 5/6. 0 times 5/6 is 0. 0 times 5/6 is 0. 6/5 times 5/6 is 1. That's exactly why I'm doing these row operations. And now let's deal with the right-hand side, the right-hand side matrix. -1/5 times 5/6 is going to be -1/6. -2/5 times 5/6 is going to give me -2/5 times 5/6 is going to give me -2/6. That is -1/3. And then 1 times 5/6 is just going to give us 5/6. Keep everything as it is. 0, 1, 3 over 5, 2 over 5, minus 1 over 5, 0, 1, 0, 4 over 5, 1 over 5, 2 over 5, and 0. So we need to do one last thing to get to identity. So if I want this matrix to look like identity, I want a 0 here and I want a 0 here. If I need to get a 0 here, I'm going to take the third row, multiply it by minus 5 over 4, add it to the first row. I'm sorry. Let's do this correctly. I want to turn this one into a 0. If I want to turn this one into a 0, I'm going to take this row, multiply it by minus 4 over 5, and add it over here. And likewise, if I want to turn this number into a 0, I'm going to take the third row, multiply it by minus 3 over 5, and add it to the second row. Okay, so I want this matrix to look like the identity. So I want this column to look like 0, 0, 1. So I already have a 1 here. If I want this to look like 0, I'm going to take the last row, multiply that by minus 4 over 5, add it over here. So in that case, that's going to turn into 0. And if I want this number to turn into 0, I'm going to take this last row, multiply that by minus 3 over 5, add it over here. In that case, this number is going to turn into 0. Let's do the arithmetic. We're taking the last row, multiplying by minus 4 over 5, adding it to the first row. 0 times minus 4 over 5 is 0, plus another 1, that's a 1. 0 times minus 4 over 5 is 0, plus another 0, that's a 0. 1 times minus 4 over 5 is minus 4 over 5, plus another 4 over 5, that's a 0. And that's exactly why I'm doing this. I'm trying to get a 0 in this position. Let's keep going. Let's apply the row operations on the whole row. Minus 1 over 6 times minus 4 over 5. Minus 4 over 6 times minus 1 over 6 times minus 4 over 5. Minus 1 over 6 times minus 4 over 5, that is 4 over 30, plus another 1 over 5. What is that going to give me? 4 over 30 plus 5 over 6, 5 over 30, sorry. 4 over 30 plus 1 over 5, that's 4 over 30 plus 5 over 30, that's going to give me, let me just do this right. Okay. I'm taking this row, multiplying by minus 4 over 5, adding it to the first row. So then we're over here. Minus 1 over 6 times 4 over 5, that is 4 over 30, plus another 1 over 5. 4 over 30 plus 1 over 5, that is 4 over 30, plus another 6 over 30. That's 10 over 30. And 10 over 30 is 1 over 3 over here. Let's take care of this one. That is 1 over 3 minus 1 over 3 times minus 4 over 5. That is 4 over 15, plus another 2 over 5. 4 over 5 times 1 over 3, minus 4 over 5 times minus 1 over 3, that's 4 over 15, plus another 2 over 5. 4 over 15 plus that's another 6 over 15, that is 10 over 15, and that is 10 over 15, that is 2 over 5, 2 over 3. Keep going. Minus 4 over 5 times 5 over 6, minus 4 over times 5 over 6, that is minus 4 over 6, minus 4 over 6 is equal to minus 2 over 3. So let's do the row operations on the second row. Take the third row, multiply that by minus 3 over 5, add it to the second row. Take the third row, multiply by minus 3 over 5, add it to the second row. 0 times minus 3 over 5 is 0, plus another 0, that's a 0. 0 times minus 3 over 5 is 0, plus another 1, that's a 1. 1 times minus 3 over 5 is minus 3 over 5, plus another 3 over 5, that's a 0. Minus 1 over 6 times 3 over 5. Minus 1 over 6 times 3 over 5, that is going to give me 1 over 10. Plus another 2 over 5. That is 1 over 10 plus 4 over 10. That is 5 over 10. That is 1/2. Good. Minus 1 over 3 times 3 over 5. Minus 1 over 3 times minus 3 over 5. That is 1 over 5. plus a minus 1 over 5. So that's going to give me a 0. Minus 1 over 3 times minus 3 over 5. That is plus 1 over 5, minus 1 over 5. That's going to give me a 0. 5 over 6 times minus 3 over 5. That is going to give us minus 1/2 plus another 0, minus 1/2. And finally, let's write down the last row as it is. Okay. So out of all of these row operations, we start with this matrix, the matrix that I wanted to invert, and the identity matrix on the right-hand side. We did a whole bunch of row operations. I ended up with this matrix, identity on the left-hand side, and some other matrix on the right-hand side, which means that the inverse of the matrix that I started with is this matrix over here. Okay. The inverse of the matrix that I started with is this matrix over here. And if you go and multiply these two matrices, you're going to get the identity matrix, but I'm not going to do that right now. Okay, so this is how we compute the inverse of a matrix by doing row operations. Again, this is something that you probably have done in high school, if not earlier. But from the perspective of developing an algorithm for solving large linear programs, this way of computing an inverse of a matrix is going to be extremely useful for us. So please keep this in mind. Please keep this in the easily accessible part of your memory. And to wrap up the linear algebra concept, we're going to say one last thing about systems of equations. And that is the following. If I take a system of linear equations and apply a whole bunch of row operations on the system of equations, the set of points that satisfies the system of equations don't change. Okay. And it's a very simple principle, but again, it's going to be something that is going to be very handy of us. Let's say it again. If I take a system of linear equations and apply a whole bunch of row operations on the system of equations, the set of points that satisfies the system of equations doesn't change. In other words, applying a set of row operations on a system of equations is completely benign. If I apply a whole bunch of row operations on a system of equations, you do not change the system of equations. If you apply a whole bunch of row operations on a system of equations, the system of equations remains equivalent. Okay, it doesn't change. So let's kind of see that principle in action. And that is again going to be quite useful for us. Let's take a system of linear equations. So let me write systems of linear equations and row operations. So let's take a system of linear equations. 2x1 plus x2 equals 4. Minus x1 plus x2 equals 1. Here's a system of linear equations. What is the set of points? Let's just plot the set of points that satisfies this system of equations. Okay. We took a simple system of linear equations, 2x1 plus x2 equals 4, minus x1 plus x2 equals 1. Let's plot the set of points that satisfies this system of linear equations. There we go. So this is x1, this is x2, it's going to be 4, 1, 2, 3, 4. Let me plot the first line. When x2 equals 0, x1 is going to be equal to 2. When x1 is equal to 0, x2 is going to be equal to 4. That's 2, 4. So the first line looks like this. Let's plot the second line. When x2 is equal to 0, x1 is going to be equal to minus 1. When x1 is equal to 0, x2 is going to be equal to 1. So the second line looks something like this. Okay. So this is the line. x1 plus x2 equals 4. Minus x1 plus x2 equals 1. And what is the set of points that satisfies the system of equations simultaneously? It's this point. It's that point. And that is the point 1, 2. So now what we want to see is, what we want to argue is, if we apply a whole bunch of row operations in the system of equations, if I apply a whole bunch of row operations in the system of equations, the set of points that satisfies the system of equations doesn't change. So that's the principle that we want to see. Okay, let's apply, arbitrary row operations on the system of equations. Like for example, let me take the first row and add it to the second row. It's completely arbitrary. Let me take the first row, add it to the second row. Just apply any row operations that you like, completely arbitrary. Let me take the first row, add it to the second row. In this case, what do I get? The first equation doesn't change. The first row doesn't change. And the second one is 2x1 minus another x1. That is going to give me an x1. x2 plus another x2. That's going to give me 2x2. And on the right-hand side, we apply 5. So I apply the row operation on my system of equations where I take the first row, add it to the second row. 2x1 minus x1, that is x1. x1 plus x, I'm sorry, x2 plus x2, that's 2x2. 4 plus 1, that's 5. Let's keep on applying a whole bunch of other row operations, completely arbitrary row operations. Let me take the second row and multiply that by minus 4 over 5 and add it to the first row. Completely arbitrary row operations, whatever you'd like. Let's take the second row, multiply by negative 4 over 5, add it to the first row. Well, if you do that, what do we get? x1 times minus 4 over 5, that is minus 4 over 5 x1, plus another 2, minus 4 over 5 plus 2, minus 4 over 5 plus 10 over 5, that is going to be 6 over 5. Keep on doing. 2 times minus 4 over 5 plus another 1, if I take care of x2. So 2 times minus 4 over 5 is 8 over 5, plus another 1. That is minus 8 over 5 plus 5 over 5. That is going to give me minus 3 over 5. So minus 3 over 5 x2 on the right-hand side. 5 times minus 4 over 5 is minus 4 plus another 4. That's a 0. Keep the other equation as it is. So I'm just applying a whole bunch of random, arbitrary, however you like, row operations that you like. I could do many, 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 many more, but I'm not gonna do many, many more and bore you. Let's stop here. So now, by applying a whole bunch of row operations on this system of equations, we obtain this system of equations. Let's plot the set of points that satisfies this last system of equations. Let's see what the set of points that satisfies this last system of equations looks like. Let's plot our first line. Minus 6 over 5x1, I'm sorry, plus 6 over 5x1, 6 over 5x1, minus 3 over 5x2, 6 over 5x1, minus 3 over 5x2 equals 0. When x2 equals 0, x1 has to be 0. When x1 is 0, x2 has to be equal to 0. So this line passes through the origin. Let's take another point. When x1 equals 1, this is 6 over 5. To make sure that I get to 0, this is 6 over 5. When x1 equals 1, x2 should be equal to 2. So this line, this first line, passes through the origin and the point 1, 2. So this is the line, 6 over 5x1 minus 3 over 5x2 equals 0. Let's plot the second line that we have here, second equation that we have here. When x2 is equal to 0, x1 is going to be equal to 5. 1, 2, 3, 4, 5. Good. When x1 is equal to 0, x2 is going to be equal to 2.5. Again, the set of points that satisfies this system of equations is still 1, 2. Okay, so the important principle that we get out of this is that if I take a system of linear equations and apply a whole bunch of row operations on the system of equations, I don't change anything. My system of equations remains equivalent to itself. The set of points that satisfy the system of equations doesn't change. So applying a whole bunch of row operations on a system of equations is completely benign. And that is a simple but a pretty important principle for us. And that's going to be extremely handy. So let's start wrapping up. So we reviewed pretty familiar linear algebra concepts in this lecture. And these linear algebra concepts are going to be very useful when we design an algorithm in the next lecture to solve large linear programs. And two particular things that we learned that we saw in this lecture are going to be important for us. One is doing row operations to compute the inverse of a matrix. And the second one is the principle that if I apply any arbitrary set of row operations into a system of equations, the system of equations remains equivalent. Applying row operations on a system of linear equations is completely benign. Applying row operations on a system of equations doesn't change the system of equations that I'm looking at. If I apply a whole bunch of row operations on a system of equations, the system of equations remains equivalent to itself. I said the same thing 3 different ways, okay? And this last principle is also going to be useful for us, okay? So this is a good time to stop. Let's stop here.